linked list implementation of a queue. So what is a queue? Queue is a linear data structure just like the arrays and the stack. It follows the first in first out principle. The insertion and deletion takes place from different ends, and insertion takes place from the rear while the deletion takes place from the front end. That makes it necessary for us to have two pointers, generally known as front and rear, which keep track of the two ends of a queue. So what are the common operations we encounter in case of a queue? One is the enqueue operation, which helps us add elements to a queue. Then you have a dequeue, which removes the frontmost element from the queue. And then you have the peek operation, which helps us view or see the topmost element without removing it. Right now, the queue implementation can be done using array or a linked list. Array implementation of the queue we have done. You can find the video in the data structure playlist. Now we would move on to the linked list implementation. See what is a linked list. Linked list is a linear data structure where each element is connected to the next and previous element, as I discussed a few moments back. Similarly, it stores elements in a chain-like fashion where each element points to the next element. Right? That pointing takes place basically in terms of storing addresses of one another that we'll be seeing in the coming slides through C programming code. Right? So similarly, linked lists store elements in random memory locations. Random memory locations means there is no need of contiguity, as is the case with the array. So array stores elements in contiguous locations. So if we have an array of say 10 integer elements, and hypothetically the base address, that means the address of the first element is 100, then we are supposed to find the next element 2 bytes apart, that is at 102. Next element at 104, next element at 106, and so on. Here I am supposing that each element takes 2 bytes. Right? So in case of linked list, the elements are stored in random memory locations that need not be contiguous. So we'll be further explaining things in the coming slides. For the timing, let us move to the last point. Linked list allows elements to be easily inserted or removed without reorganizing the entire structure. Right? So we can take an element in between without reorganizing the entire structure. Similarly, for deletion, we can delete an item or the element of the linked list in the middle without disturbing the organization of the entire structure. Right? Things would get clear when we discuss the linked list in detail. For the time being, we will be concentrating on the topic at hand, which is the linked list implementation of a stack. So coming on to the implementation part. So before doing the implementation part, let us see some key concepts that we should know first before going on to the actual implementation. So the first one is the node. So what is a node? Each element in a linked list is called a node. So it basically has two parts, the data part and the link part. Data stores the actual data that needs to be stored, and then you have a link part which stores the address of the next element, which is generally represented by a pointer that we'll be seeing shortly. So as far as the implementation is concerned, we'll be using the services of a structure variable, which is a user-defined data type, just like a class. So here the structure consists of the data part and the link part. So you can see a pointer representation or the notation here. That means that this part or this part in the picture is basically a pointer. And pointer, as you know, is a variable which stores address of other variables, and you assign a data type to the pointer of the variable of which it is storing the value of. So In this case, struct node type pointer means that this part or this part would be storing address of another struct node variable, just like the one defined here, right? Since each node is a composite a kind of entity wherein we have two components, one is the data and another is the link part, it makes it imperative for us to declare the variable as a composite data type. So structure here represents a composite data type which is itself made of further data types like int and the pointer part. So you can have many more uh, data items which are generally called members of the structure in case of a structure. So you can have a struct student, then you can declare int roll number and name and address, parentage, and etc. Those all would be referred to as the members of that structure student, right? Same way you can store the details of an employee, and we can call that struct as struct employee. Then you can have id, you can have the first name, last name, salary component, and the other associated things. So here also you have two members. One is the data part, as you can see here, and another is the link part that you can see it here, right? So what is basically a linked list? We can move on to that. So a linked list, as you can see here, so this is a node, this is a node, this is a node, and this is a node, and this is also a node, right? So here is the data part 10, 20, 30, 40, and 50, and this is the link part. So I have assigned some hypothetical addresses to each node. So here writing 111 here means that this node has been declared, or it would be accessible at the memory location of 111. Obviously this is a hypothetical value, right? So for understanding purposes I have written here 111 as the address of this node, right? So same way this node has been declared at the address 222 and so on, right? Another thing that is important to mention here is that the link part generally makes a connection or the link to the next or the previous node. So here in this case, writing a 222 here means that this node is storing the address of this node, right? So that creates a link. So this arrow is basically an indication that this node is connected, or it is associated with this address. How? Because it has stored address of that node. Similarly, this node and this node are supposedly connected because this node has stored address of this nodes, and same way here also this 444 is being stored here, this 555 is being stored here. Now understand that this address, these are all addresses. So how they can be accessible? They can be accessed by using a pointer. So that pointer would be struct node type. So this 111 as an address is not address of some integer or character or a float variable, in which case I would have written an int or a float or a char here. So I hope you understood that. What does this struct node asterisk mean? This struct node asterisk means that these addresses, or the address that would be stored here, would be of some node. So here that has been vindicated or justified because I have stored this 222 here, which is the address of another node, like this one itself is a node, right? So this is let us compare this to, say, the concept of the array. I have here declared an array of the type of integer, and supposedly I would be restricting my discussions to 10 elements only. You can have a bigger array also. So if I can draw it, so I have taken here the array with 5 elements: 10, 20, 30, 40, and 50. So here is the, as you may be aware of the fact that the individual array elements are accessed using a unique number which is known as index. So index starts from 0. So 0th cell would be this would be 1, this would be 2, this would be 3, and the process will go on. So here I have shown some hypothetical addresses, like if this element, the first element of this array is stored at 100, the next element would be stored at 102, next at 104, and so on. Here I have stored those elements 2 bytes apart because the array has been declared as integer, right? So supposedly here I'm assuming that the integer in most of the cases takes 2 bytes and integer value. So that is why, so this 10 would be stored in the memory at the byte 100 and 101. That is where the next element would start. That means it would start at 102 and it would take another byte at 103. Then we will have this 30 at 104 and 105, since each value would be spanning 2 bytes, being an integer array. So this is what I was referring when I told you that the arrays store elements in contiguous locations, which in this case isn't true. In case of linked list, even though I have shown them as being stored in the contiguous locations or the subsequent locations, which may not be the case. So if this 111 is here, this 222 may be at some other location in the memory. This 33 would be at some other. So it is basically this address which is being stored that is important to maintain an association between the nodes rather than having them in contiguous locations. So this 1 1, this 2 2, this 3 3, they need not be contiguous. They can be any locations in the memory. So important thing is to store addresses of one another rather than being adjacent to each other. Right? So coming to the memory allocation, this is in continuation with the key concepts that we are taking up. Right? We should know some things or some definitions first. Then we can move on to the linked list implementation. So you will have to be patient for a bit more till we reach there. So memory allocation basically is of the type of static memory allocation and the dynamic memory allocation. In fact, we will be doing things this way when we implement things when we implement stack using a linked list. But we need to know the associated concept sets well. So static memory allocation is done before the program execution, while as the dynamic memory allocation is done during the program execution. So if I say I declared a variable called a with a value of 1, it would be declared like this. So you have the name of this cell as a, 10 would be stored there, and this is a hypothetical address I am assigning. You can obviously take any value or the address for understanding purposes or for referencing purposes, right? So I'm saying that this a has been declared at 1 FFE location in the memory, and a value of 10 is stored at that location, right? So if I have another variable p, since you know that a pointer variable is prefixed with an asterisk sign to mark it as a pointer, and pointer stores address of other variables. So that is what I am doing here. I am assigning address of a to this p. Now since I am assigning address of some variable, it makes it a pointer variable, or it makes it a point to declare it as a pointer variable. Second, and the most important thing is that since I am assigning the address of an integer, since a is an integer variable, so if I am assigning address of an integer variable to a pointer variable, that pointer variable should also be declared as an integer. That I was alluding to in the previous slide, that if you are storing address of a structure variable, that pointer variable also should be declared as a structure variable, right? So since p is storing address of a here, which is an integer, so that way we need to assign p a data type of it, or it is to be declared as a integer variable or integer pointer. So if we can see pictorially, so we are seeing here that p has been declared and it is being allocated or declared at a memory location 2FFE. Again, a hypothetical value I am taking, but the important thing is, what are the contents of P? Contents of P are 1FFE, which is the address of A. So I am assigning address of A to P, right? This is very important in the context of what we will be discussing shortly. That is the implementation of stack using linked list, right? Right? So coming to the dynamic memory allocation, which is done during program execution. What does that mean? That means we'll have some sort of functions or the instructions which would be executed at runtime, and they would be doing the memory allocation part. So there is a function in C which is called malloc. Malloc means memory allocation, which allocates memory, right? And the quantity or the amount of memory that is to be allocated is written within the parenthesis. That means that the malloc function takes integer as an argument. Since 2, we cannot write 2.5. So it isn't float, it is basically integer. So if someone asks you what is the type of this argument which is being passed to malloc function, the answer is integer. So malloc simply means allocates memory, and malloc2 simply means that you are allocating 2 bytes of memory. Now, what does this int a, when we do write int a, this also allocates 2 bytes of memory if we are assuming that integer takes 2 bytes, right? So this is doing the same. Malloc2 is doing the same. Then what is the difference? Difference is that here you have named that location as A, while as here you have allocated 2 bytes of memory, but you have not assigned a label or the name to those 2 bytes that you have allocated. So we'll be elaborating on things shortly. Let us move to this second example. So malloc4 means allocating 4 bytes. Why I'm writing 4? Here I am alluding to a integer declaration. Here I am alluding to a declaration of a float which supposedly takes 4 bytes, right? But generally we don't allocate memory dynamically this way. That means we don't write malloc and then some integer, random integer within the brackets. So you can have an argument of why not do malloc 3, which would supposedly do a memory allocation of 3 bytes. But 3 bytes is generally not a standard size, even though 2 and 4 are to some extent, right? So what is the point here? Point here is that you do memory allocation in terms of standard sizes or the data types. So I'll be replacing these numeric values with another function in C which is known as sizeof. So sizeof int gives you 2. So malloc 2. So it is equivalent to this writing, but writing it in a standard way, right? So if I am declaring some float variable at runtime, kind of. That means 4 bytes I am allocating. So I can write malloc size of float, malloc size of char, and so on. And malloc size of struct node is no exception. In which case, the total size of the structure, if it is say x, so x bytes of memory would be allocated, right? So we'll be discussing that shortly. So for the time being, let us concentrate on this integer part or the float part, right? So if you are writing malloc size of int, it means memory allocation of 2 bytes would be done. If I write malloc size of float, it means a memory allocation of 4 bytes should be done, and same for a character. Now what is this p? As I discussed here, in this case, that you would be declaring memory, but you would not be assigning a value or a label to it. That is what we are doing here. If we write only malloc size of int, 2 bytes would be allocated, but there won't be any label which would be pointing to those two allocated or declared bytes. So this p would store the address of those two bytes that were allocated. Or in short, to generalize things, when we write malloc, we do the declaration of memory or allocation of memory, but the starting address is stored at the variable that you have assigned it to, right? So in this case, when I write p is equal to, it means allocation would be done and the starting address would be stored by p, right? Now to check your knowledge, what would be the type of this p? Data type of this p? It would be integer, because you are allocating memory to an integer data type, right? Or size of 2. So this p would also be declared as an integer, right? So it is kind of this sort of declaration would be perfect in this case also, right? So if you are doing malloc size of float, then this p would be declared as a float pointer, of course, right? Now coming to the dynamic memory allocation for a node. So previously you saw if we will have to allocate memory for an integer or a float variable or the basic types. Now for a structure, how the memory allocation would be done, right? So if you are writing struct node, so this basically is a structure variable consisting of two parts. The integer part is the data, and there is a pointer part. As you would be aware of the fact that any pointer variable takes 2 bytes to store. So 2 bytes of this and 2 bytes of this int. So that would be the total size of this struct node. So if we will write that malloc memory allocation is being done of what size of struct node. What is struct node size? 4 bytes, as we just discussed. So malloc of 4, that means allocation of 4 bytes should be done, and the starting address would be stored at sp, which is a pointer variable of the type of struct node. As I just discussed, that this sp should be the same, or you can take it as a trick that this sp's type should be same as what you are writing here, size of within the brackets. So within the brackets I have written struct node, so this sp would be a pointer of that type. Just like we in the previous example wrote int asterisk p, then we wrote size of int. So what is written here in the bracket should be the data type of this pointer, also in this case the node type, right? Now let's understand a bit further, right? So sp is a variable, a pointer type variable, which is supposed to store address of certain node, right? I leave this for the moment. So this SP has been declared at 3FFE, a hypothetical address. Now, when you did this memory allocation, so the memory allocation is done at this location, say 00FE. So what is the address of the allocated node? I would say node, because there are two cells. It has been declared in this context, right? So this would be my data part and this would be my link part. So collectively, it is a node which has been allocated a memory of 00FE or at 00FE, of course 4 bytes, right? So the address of this node would be stored here. Why? because I have assigned this by using this is equal to, I have assigned this address to SP. So the contents of SP would be 00FE, which is the address of this allocated node. Right? Right? So 00FE. Now, how to access? I'm sure you would have already done this while studying structures. I'm just polishing the things off, right? So when you access certain memory location, as far as this structure variable is concerned, you use the pointer, you use this arrow when you are doing dynamic memory allocation. That means when you have declared the memory for a structure variable dynamically, then you use this pointer operator. So SP means SP arrow data means, what is SP here? SP here is the contents. Just like when we say A and we store 10 here, then we print A, it stores a it prints contents of that A cell, which would be 10 in this example. Similarly, when I say SP, it means 00FE, the contents stored at that location, right? So this means the data part of SP or 00FE, which would be right here. So I am assigning the data part of the 00FE memory location to 3, right? By virtue of this statement. Similarly, the link part I am assigning to null. This is how you do things when you have declared a structure variable dynamically and you are using pointers, right? So now on to the linked list implementation of a queue. So we need the service of a structure variable which has been named as struct node in this case, which comprises of two data members. One is the data part and another is the link part as shown in the figure. Furthermore, we would need the services of two variables called front and rear, both of which have been initialized to null, right? This is to say that there is currently no node which has been allocated, or we can say the queue is empty, right? We would need service of some other variables also, which in this case have been declared as T and P. Now onto the code. So I am writing the code here for the enqueue function. As I told you already that enqueue is an operation which adds elements to a queue. So that element which needs to be added has been passed here from the calling function, which could be a main function or any other function. So that n, that value, we would be assigning to this data part and would be doing the linking part as we go on. So for the time being, let us concentrate on the second instruction, which basically allocates memory for a node like this, as we have already discussed, the starting address of which has been stored in P. So here I am supposing that the new node was allocated at an address of 111, a fictitious address, as I said again and again, right? So I'm also assuming that from the calling function we have got a value of 3 which has been stored in this n, and the same n has been assigned to the data part of the newly allocated node. So we can see it here, right? Then we are doing what? We have initialized this link part to null, as you can see from the figure. Now the function enqueue function would not end here. We will need to check certain things. Let us go to that. So here I am saying if f is equal to null and r is equal to null, that means both the pointers front as well as rear are pointing to null, right? In that case we would be assigning to we would be assigning f is equal to p. Correct it here, it is f is equal to p, not f is equal to p, right? So I am saying if f is equal to null and r is equal to null, which would be true in this case because they have been initialized to null and null to start with, right? right? So our first would now be pointing to P. What is P? P is the address of the newly allocated node, which is 111, right? So F would now point to 111. Fair enough again, because this is our frontmost element or the topmost element or the first element, right? So else part, we are saying we would not discuss the else part for the time being, because if has been executed or if stands true at this point of time, or in other words you can say that this function what it is checking is that it is asking us if this is the first node that is being allocated, right? Because in that case only our F and R both would be pointing to null. So here if is confirming that is this the first node that has been created or allocated, because as we discussed earlier also that this first node is a special case, as was the case with array implementation of Q, when we said that the first element of an array in case of a queue, the first element is your frontmost element as well as the rearmost element, right? So this first node would always represent a special case wherein both front and rear would be pointing to the same node or the same value. So leave this else for the moment, go to this. Here R is equal to P means rear is now pointing to P also, right? That has been shown here. So my front would be 111 and my rear would be 111 in this case, because P is 111. So F we have assigned P as well as R we have assigned P also, right? So assume that we are calling this function again with a different value. So what would be done? A new node would be allocated. So here I am assuming that we have been passed a value of 5 in this, and that n has been assigned to data as we did in this case also, right? What is the link part? That also has been assigned to null, right? Right, now coming on to the if part. If F is equal to null and R is equal to null, which would be false in this case, because both F as well as R now are pointing towards what? 111, right? So this time control would go to else part. So would be doing R pointer link, that means link part of R. What is R? R is 111. So the link part of 111. So this link part of 111 would be equal to P. What is P currently? It is the address of the latest node which was allocated, which is 222. So this 222 would be stored here, right? And of course, since we are now updating rear to the next node, so we are saying R is equal to P. So R would now point to this 222, and obviously front would continue to point to this node, because this would now remain the frontmost element if 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 a number of insertions would take place in this queue. So assume that this happens the third time. That means the enqueue function has been called now for the third time. So again a node would be allocated at a fictitious address, for example 333, which would be pointed to by P. Now the data part would be initialized with the value that has been passed to this function. Let us assume it is a 2, right? And you would assign the link part a null. Now this if you should remember that this would be true only for the first node. So rest of the nodes or the subsequent nodes, only this else part would get executed. So in this case also, remember that R currently stands at 222. So we are basically assigning the link part of 222 a value of P, which in this case is 3. So this 333 would come here and the rear would come here, because we are saying rear is equal to P, right? And the process will go on. So I'm here taking an example of 5 nodes. So this is the last step wherein P was 555, right? And its address would be stored by its adjacent node, previous adjacent node, which would be this node. So it is storing the address of 555. So this part, p arrow link is equal to null, comes into effect here, and it tells that there is no subsequent or adjacent node once we leave this function. So this would be the creation of a queue using linked list. Right? Now, how to display contents of a queue? Say for the same set of values, this would be our front and this would be our rear. Right? Now, remember that the deletion or the traversing starts from the front. So as far as code goes, first we will check whether f and r are null, both null. Then it would be a case of underflow, or you will print a message that the queue is empty. Else you would be storing the value of f, that means this f or the front, to p, a temporary variable, so that we can use it in the while loop, advance this t instead of f. As we saw in case of stacks also, we preserved the value of top so that we always remember the value of top. Similarly, in this case, we need to remember the values of front and rear, and if and when these variables are needed for some intermediate operations, we can use some temporary values, which is what we have done here. So f has been assigned to t. Now we are saying while t not equal to null, so t would be now 1 1 1. So till it reaches null, we will be continuing to print the value at that node. So t arrow node means this 1 1 1 nodes data part, so 3 would be printed. Right? Now you need to add, if you forgot this instruction, it would make the t point to this node continuously without updating it. So we need to update it to the next node. How? We are assigning t the link part of t. So what is the link part of t? 2 2 2. So t would be assigned 2 2 2, which advanced it to this node. Right? So going back to the while loop, so t is 2 2 2, which is not equal to null, so it would be printing the data part of t. So data part of t is data part of 2 2 2, which is this 5. Right? And then we would do the same for this node and this node and this node till the contents are exhausted, or we have traversed the whole queue. So over to the dequeue function. What does the dequeue function do? It basically removes the frontmost element from the queue and updates the pointer to the next frontmost element. So in this case, the example we have been using all the way. So front is 1 1 1 and your rear is supposedly 5 5 5. What should happen in this case? First we will check whether front and rear are having some non-null values, otherwise you will print a message of underflow. So in the else part would be what? Storing what is f? F is 1 1 1. What is 1 1 1 is data part? 3. So 3 would be storing at v, a temporary variable, of course. Then you are assigning the front, that means 1 1 1, to t, again a temporary variable. Then we are advancing the front pointer to the friend's link. What is friend's link? 2 2 2. So now f would point to 2 2 2. So for the remainder of the operations, we would have the front pointing to 2 2 2. Now two things need to be done. One is to remove this, since this has been detached, kind of detached from this queue, or we need to detach it, would free its memory. So we are freeing what? T, right? We cannot free f because it has been advanced to 2 2 2. So that is why I saved friend's value to t earlier, right? And the next thing which needs to be done is you should print the value of v, which is the original frontmost elements data part, or the value stored at that location, right? So that would be 3, right? So similarly, so the front would now point to 2 2 2. So the last function that would be taking up is the peek function. As discussed already, the peek function helps you to see or view the contents of the friendmost element or the value at the friendmost uh, node, right? So for the same set of values, parent is 111, rear is 555, check the underflow condition. Otherwise, print the value at the friendmost node's data part, which would again in this case would be 3, right?